Good morning and thank you for joining. My name is Justin Sears, Product Marketing Manager at Hortonworks. It's my pleasure to host our 8-webinar series entitled Discover HDP 2.2, covering all the new capabilities for Enterprise Hadoop delivered in Hortonworks Data Platform version 2.2. Today's Even Faster SQL Queries with Apache Hive and Stinger.next is the second webinar in the series. For a summary and the video recording of last week's first webinar, look for the blog on our website entitled Discover HDP 2.2, Comprehensive Hadoop Security with Apache Ranger and Apache Knox. I'll be your host today, and I'm joined by two Apache Hive experts. Alan Gates is one of the founders of Hortonworks and also a committer and PMC member for the Apache Hive project. Alan is one of the early architects of Apache Hadoop, and he led the effort to take Apache Pig from Yahoo Labs and make it an Apache open source project. Raj Baines is Hortonworks Senior Manager of Product Management. Raj is responsible for management of Apache Hive within Hortonworks Data Platform. Here's today's agenda. We'll begin with an overview of the Stinger.next initiative, which builds on the successful completion of the original Stinger initiative earlier this year. Stinger.next aims to further improve Apache Hive's capabilities for speed, scale, and SQL. Then we'll give an overview of Apache Hive version 0.14. We'll discuss three important areas of innovation in Hive 14. For SQL, we'll go through transactions with ACID semantics. For speed, we'll discuss the cost-based optimizer for star and bushy joins. And for scale, we'll cover dynamic query optimization. Finally, we'll discuss what's coming up in Stinger.next, and we'll make sure to finish with enough time for Q&A. We've got 30 minutes, so we're going to move quickly. All attendee phone lines have been muted. If you have questions during the presentation, please send them to Raj Baines in WebEx chat. We will take time to answer those at the end of the call. And if we don't have time to answer all of those questions, we will include a full Q&A in an upcoming blog post about this call. Let me set the stage for Alan and Raj. The data center is in the process of replatforming to include Enterprise Hadoop as a core component in the modern data architecture. Business, technical, and financial factors are driving this shift. On the business side, greater data availability allows decision makers to move from reactive rear-view mirror analytics to proactive interactions that reduce costs and improve loyalty with customers, partners, suppliers, and employees. Technical teams are adopting Hadoop in response to the exponential growth in data, much of it in newer, less structured formats from sensor, geolocation, clickstream, or social media sources. And finally, companies are responding to the growing costs of data systems that are consuming an increasing share of IT expenditures. Hadoop's commodity hardware and open source software relieve that pressure and free economic resources for other opportunities. For example, Hortonworks customer TrueCar stores and processes data in HDP at an effective cost of 23 cents per gigabyte per month, compared to the alternative of $19 per gigabyte per month with a traditional platform. Enterprise customers that address these needs with traditional vendors can find an inequitable balance of power. Apache Hadoop brings new options and helps rebalance that equation in your favor. Here are some of the new types of data I mentioned. These are difficult to efficiently store and process with a schema on write column and row storage platform, precisely because their data structures vary in unpredictable ways. Apache Hadoop has a schema on read architecture. All types of data can be stored in Hadoop regardless of source or structure, and then the query determines what data best answers the analyst or data scientist's question. HDP helps our customers make the shift from a reactive post-transaction approach to data towards a more proactive pre-decision approach to interactions with customers, partners, suppliers, and employees. Again, no matter the vertical, this transition is happening. Advertisers move from mass branding, targeting the median customer, towards one-to-one personalized targeting. Financial companies move from educated investing to automated algorithms that find new, complex opportunities and present them to investors with enough time to take action. Healthcare providers and pharmaceutical companies can more precisely tailor treatment protocols and drugs according to genomics, age, gender, medical history, and a long list of other factors that affect outcomes. Retailers are offering personalized experiences online or in the store according to who each shopper is and what he or she prefers to buy. And telcos move from fixing broken transmission equipment to replacing it before it breaks at a much lower cost. Here is the modern data architecture with Hadoop that makes those precise, proactive decisions possible. It consolidates data that might currently exist in many silos managed by different business groups. It allows you to manage a single data set on a single cluster and reduces redundant IT investment in multiple platforms. With all of the data in one place, it supports common services for security, governance, and operations that can be managed centrally, reducing cost and improving consistency. The modern data architecture also preserves existing investment in current tools and platforms. Hortonworks has taken the lead to partner with other data center technology vendors to make sure that Hadoop is a +1 with existing investments in Microsoft, Teradata, HP, SAP, Oracle, and many other leading technology vendors. Choosing Hortonworks Data Platform does not require you to abandon any other technology that's already working well for you. Rather, the modern data architecture lets you handle each data workload with the best technology in a way that's seamless to your end users, giving you a single view of your customer, your product, and your supply chain. Yarn is the architectural center of Hadoop. It makes Hadoop a common data platform that can be accessed by many applications at once, supporting multi-tenant access and processing. Yarn makes batch, interactive, and real-time processing possible on one data set in a single, highly available cluster. Yarn also provides a single standard for third-party ISV data access tools. At Hortonworks, we make it easy for our partners to develop applications that work with Yarn, and then we certify those partner applications as Yarn ready. Enterprise Hadoop also requires a central set of services for cluster governance, operations, and security. Everything that plugs into Hadoop inherits those services. HDP 2.2 delivers enterprise Hadoop and vertical integration with Yarn and HDFS. This ensures that engines can run reliably and respectfully in a Yarn-based cluster. Features throughout the various HDP stack components facilitate this vertical integration. HDP 2.2 with Yarn as its architectural center also integrates horizontally with key enterprise services for governance, security, and operations. This ensures that those enterprise services apply consistently across the entire Hadoop stack. It also integrates with existing data center solutions for those key requirements. So to sum up, HDP 2.2 delivers the power of Yarn for dynamic resource allocation and multiple workloads, with comprehensive enterprise capabilities for governance, security, and operations. And it enables broad ecosystem adoption of enterprise Hadoop with the widest range of deployment options on Linux or Windows, on-premise, or in the cloud. Today's webinar will focus specifically on one type of data access, interactive SQL queries with Apache Hive. Hive is the de facto standard for interactive SQL queries over petabytes of data in Hadoop. We will cover other types of data access in Hadoop and the other components of HDP 2.2 in the remaining 6 webinars in the series. Now I'll turn it over to Alan Gates. He'll start us off by giving an introduction to the Stinger.net initiative and its goals. Please remember to send Raj Baines any questions in chat and we'll answer those at the end. Take it away, Alan.
Good morning, everyone, and thanks for joining us. So I wanted to start by just introducing a little of what we want to do in Stinger.next, and then Raj and I will walk through some of the exciting features that are coming soon from in Apache Hive.
Alan, this is Justin. Sorry to interrupt. Could you show the full screen? Lower left.
Better?
Yes, there we go. Thank you.
All right, excellent. Sorry about that. Okay, so in this slide we see on the left, what has been in Stinger, and then things we want to add in Stinger.next. So the focus of the Stinger initiative for the Hive community was to take Hive from its ETL MapReduce bound roots and really start to transform it into the database front end that you want to have for your modern analytics work. And this played out along 3 dimensions, as Justin already mentioned: speed, scale, and SQL. And so you saw us move on all 3 of those dimensions in Hive 11, 12, and 13, which got branded the Stinger Initiative, where we sped up Hive from completely batch to being interactive timelines where you could sit there and interact with it, and queries will return in a few seconds now for smaller data sets. We substantially increased the SQL support to add windowing functions, new data, standard SQL data types, all that kind of work, so that you could start to use Hive in the SQL applications that your analysts and your tools want to use it in, and while still maintaining the scale that Hive is known for. On the right here in this slide, you'll see how we want to continue to move along all 3 of those dimensions in the Stinger.next. We want to continue to scale well. In fact, we want to even improve our scale there. We want to move our performance to where queries over very small data sets are even returning in sub-second time frames. And we want to continue to grow SQL, adding things like transactions so that you can update and delete data in your data store, and continue to grow our SQL coverage. So let's just dive into what some of those are real quickly. And as soon as I figure out how to make the slides move forward. There we go. All right. So the first one we will talk about here are use cases for transactions. Why would you want to add transactions to this? So in the past, Hive had the ability to insert new partitions, to create new data, and that was transactional in as much as a user either saw that new partition or they didn't. But because HDFS is write once you created data, there was no way to update it. There was no way to delete individual rows. You could drop full partitions from your table, but that was about it. And even inserting new records into an existing partition, it could be done, but it was not possible to do in a ACID compliant way, by which I mean a way that you either knew a reader would or wouldn't see that data. It was hard to determine whether readers got to see the data that you were adding if you started appending to existing partitions. So we wanted to change that. We wanted to bring standard insert, update, and delete to Hive, but we want to be clear about what use cases we're going for here, right? We're not trying to turn Hive into an OLTP engine to do lots of little transactions, like if you were trying to write a shopping cart app for your website or something. That's not at all what we're going after here. What we are going after is making Hive support those standard data warehousing type use cases, which is, even in a data warehouse, sometimes your data changes. Sometimes you need to correct wrong data that was put in there. You need to, just fix the data that was incorrectly imported. Or you may have dimension tables that change over time. For example, if you're tracking, maybe, you're a retailer and you're tracking physical stores and your store moves across the street, or its zip code zone changes, and so you need to, update its zip code in the table. All those kinds of things you'd like to have an update statement for. And occasionally you need to remove records from your data also for legal compliance. You may need to remove customer records from your data. All those things you'd like to be able to go in and do updates and deletes on your data. Those are the kind of things that we want to support. We also want to support ingest of operational data from OLTP systems into your data warehouse, where Hive can be used to very quickly ingest that, to stream that in with some kind of tool like Storm or something like that, and then Hive can make that available. We want that to be available near real time instead of in an hourly or daily batch the way it's done today. So how did we do this? How do you make transactions work on a system that is sits on top of a file system that's write once and then read many times. And it turns out the industry has actually solved this problem a number of times, because even if you can write to your file system again, even if you can do random reads and writes, it's so expensive on large data sets that you really, really don't want to do that. So a very standard way to do this is you have your original data, which you see here in this diagram as one original file. So that's the original insert or whatever of data into this table or partition. And then as updates and deletes or new inserts come along, you don't touch the base file, the original file. You write those on the side in a Delta file. And then when the reader comes along to read that, that reader is responsible for then resolving, okay, which version of this row should I see? Because inside that Delta file, in addition to the row ID to tell the reader what row this matches with, is also transaction information. So the reader even knows, should I or should I not see this data, right? Because that transaction may not have been committed yet, or it may have been committed before that reader, or sorry, after that reader started. So for that reader, it's still not a valid record. So the reader needs to do that resolution between the Delta file and that original file and decide which version of the row to show, or if it's a delete in the Delta file, to not show the row at all. The reader does that. That works just fine, but over time, if you get too many records in the Delta file or you get too many Delta files, your reads are going to start to slow down. So you need to go behind and compact this. So we have added a compactor to Hive to go behind the scenes. You as a user don't have to start this or worry about it at all, and actually rewrite those Delta files and the base into a new base file or new original file that can then be read directly by the reader without having to do the merges. That happens in the background based on sizes of the Delta files and number of Delta files, that kind of stuff. The system makes a determination of when that needs to be done. And it's done in a way that it's completely does not interrupt the rest of the online processing. Other users can continue to read and write while that compaction is going on without any impact. So what of this work is done? The very first phase of this was released in Hive 13, which was the ability to ingest inserts only via Flume or other streaming agents, though the first implementation was done with Flume, so that you could connect your operational systems, your logs, those kinds of things, and ingest that data quickly into Hive. That was released in Hive 13. In Hive 14, which will hopefully be out soon, like in the next few weeks to a month, we are adding insert, update, and delete to the language. So insert obviously was already there some, but we're expanding insert to allow insert values and to better support insert into existing partitions. Update and delete are completely new commands, and those are SQL standard. They were done in a SQL standard way inside Hive. So those will be added. In this phase, all insert, update, and delete are all auto commit. There's no begin or commit or rollback yet. That will be added in a future phase where we'll enable you to say begin transaction, do a bunch, do a number of operations, and then do a commit or a rollback. That's not there yet, but it will be added soon. So that is transactions and the work we're doing to add that. I'm going to now pass control over to Raj to talk about some of the work we're doing on the cost-based optimizer.
Hi, everybody. I'm Raj Baines. So cost-based optimizer is something that is become a priority for us because as our users are using us more and more for complex queries, so we need a better optimization so that the users can just move their complex queries without worrying too much about how they're optimized and so on. Also, it allows Hive to be used better with the BI tools because the BI tools are automatically generated queries because those queries might not be written that well, but if there's a strong cost-based optimizer, you're going to get good results. So it's an area we are heavily investing in. And what I'll do now is go through one example of a complex join that we optimize to show the kind of things that are coming in this release. So here is a query, it's query 17 from TPC-DS. The things to see here is that there is, a whole bunch of tables that are joined, and I'll come to the details of that in a second. You have a bunch of filters, group bys, order bys, a bunch of aggregations that you can see in the select. So for this query has three big fact tables. So you might have seen in the public domain, it's easy to optimize what are star queries, which is one big fact table and then a few small dimension tables, right? You see there are entire benchmarks in the public domain where there are handpicked queries with that. But this is a more difficult query because you have three large fact tables and your intermediate data size is going to be huge. So the order of join that you pick is very important. So items and stores are medium-sized tables, and you have date dimension, which each join with the large fact table. So you've got D1, D2, and D3. So the important thing here is that they have filters. The D1, D2, and D3 have filters which are on quarters, and so they can reduce the size of the fact tables if joined correctly. So if you don't use the cost-based optimizer, what you get is, or even with some simpler cost-based optimizers, what you get is a left deep tree. So here the tree is drawn. It's reverse of how we draw trees traditionally in computer science. This is more like a real tree. So here what you have is the plan without CBO. So you have map 12 and map 9 happening first, which are joining store returns and store sales, which are two large tables. Right after that, map 2 comes in, which joins the third large table, catalog sales. And then all the tables are joined one by one, and the date dimension tables, which have filters on them, are coming in late and then filtering a whole lot of rows out. So this is obviously not the most optimal plan because you don't want to scan the whole large tables. What happens in the new cost-based optimizer is that we generate what is called a bushy tree. So the things to note here are, one, that there are multiple different branches of the tree that can start in parallel. So it's not happening one by one. And the second thing is that you'll see that at the top there is map 9, map 1, and map 2, which are the date dimension tables, and they are joined with the three large fact tables: catalog sales, store sales, and store returns. So the first thing we are doing is we're taking the filters on the dimension tables and making sure that we have to read the minimum rows out of the big fact tables. And then we join the fact tables, two of them first and the third later. So the question is, this of course reduces the amount of data that moves around the system. So let's look at the performance we get out of this. So we used a 30 terabyte data set, and we used it on our 20 node cluster. And so there's about 186 million input records. And the time with CBO off is about 3 hours. And it comes down to about 20 minutes with CBO on. So you see a huge improvement in the time taken. And by reducing the data early, the intermediate data is going from about 5 terabytes to 275 GB, which is a huge improvement. And so the chart shows the elapsed time, the intermediate data, and the total output records, which includes the input records. And we have a huge improvement on all of those fronts. So the second thing I want to talk about is the new pattern of dynamic query optimization. So I believe that big data requires dynamic query optimization. So what happens is you're in the query optimizer trying to figure out, how much data is going to go, be there in the middle of the query. So let's say you do 5 or 7 joins, right? And after that, you have to do a group by or something. And at that time, we are trying to figure out, should I use 3 nodes? should I use 10 nodes, right? It really depends on how much intermediate data is being produced. And to get that value right statically early in the compiler is just very difficult. So what we're starting to do is to say, well, just in the middle of while your query is being computed, let's just at runtime see those things and make changes to the query as the query is running. So this is something called auto-reducer parallelism. So here on the top right, we have in the green and orange, we have map and reduce tasks. And in blue, you have the app master, which is controlling the execution. And after the map tasks run, they send the data size statistics to the app master, sharing how much intermediate data is being produced. And in this case, initially, we had thought that we are going to use 3 reducers based on the size of the data. But as the query is running, we realized that much lesser intermediate data was produced than we had expected. So the app master kills one of the reducers, and then the data that was going to go to that one, as you can see in the image at the bottom, is being redirected to one of the existing reducers. So this allows us at runtime to pick the right number of reducers and so on. So we get, this graph just shows some performance improvements we get over a sample query. And the second one is dynamic partition pruning. So this is where you have, let's say your table is partitioned by date. So you have a partition per different date or something. And this is where you don't know initially which partitions are going to be used for a join or some other operation. But we know that there is, let's say there is a dimension table on which a filter is going to be applied. And after that, I'll know how many, which all partitions need to be scanned. So here we do the same thing. We pass that information to the app master, which then scans only the partitions that are required. And this also gives, this is PPCDS query 3, and here we get, about a shave of half the time by pruning out partitions that are not needed. And at the end, I'll talk about, Alan talked about Stinger.next and what changes are coming with Stinger.next, and I'll talk about the timeline of the delivery of Stinger.next. So the first release, which is going to be out in a few weeks, is themed on beyond read-only. So it will be adding transactions, as Alan talked about. Temporary tables will be there. We haven't talked about that. We talked about cost-based optimizer, and there's a whole bunch of improvements in execution, like the dynamic queries that I showed. So in the next release, which is expected to come in the around first half of next year, we'll be bringing sub-second queries with a new component called LLAP, which will work with days to make your queries return in under a second. We'll add Hive Spark machine learning integration, which will allow you to run machine learning from Hive on Hive data. And then we'll do, Alan talked about operational reporting from a transactional database by doing replication with Hive. And then there will be continuing SQL and CBO improvements. So that's all coming in the first half of 2015. And the second half of 2015, the next release will be focused on richer analytics. So that's where we are going forward towards being compatible with SQL 2011 analytics. We are planning to add things like materialized views and cross-geo queries. Cross-geo queries are queries which span multiple Hadoop clusters, which might be across geography. And then the LLAP, which will be added in the first half, it will be integrated well with Yarn for workload management in the second half. So this is the plan for Stinger.next, and we believe at the end of it, you will have is a Hive that can handle ETL, batch reporting, interactive queries, all three really well with very wide SQL coverage that you expect from any traditional database warehouse system. So with that, let me move on to question and answer. Thank you, Justin.
Thanks, Raj. What kind of questions have been coming in from the audience?
We have a couple questions so far. One, we had a question on whether you can access the data that's been stored, that's been updated and deleted outside of Hive, if you have to use Hive for that. And the answer to that is, right now, it has not been integrated with HCatalog. So you can use Hive, or it actually just works off of the ORC storage format. So you could use ORC input format directly. But that is something we plan to integrate more tightly with HCatalog, with Pig, and other systems. That's kind of in a future phase. And then another question we got was whether there's a bright future for integrating Hive and query against HBase. And the answer to that is yes. We are starting to work on that and think about that. And I would refer you to our Hive and HBase Better Together blog that we published last month, or maybe earlier this month, I forget, that talked about kind of how we want to approach that and going forward. So those, I believe, are the questions we've gotten so far. Oh, one more. What is what we've seen update and delete in the sandbox already included in HDP, or is what we've seen of update and delete already included in the HDP 2.2 sandbox? I don't think it was in the, I don't actually know. Do you know the answer to that?
Yeah, so it works in the sandbox, but you'll have to do a bunch of changes. We'll post an updated sandbox where there is an example that walks you through it, and that will be coming very soon. Yeah.
All right, maybe time for one more question, if there's any others there.
We don't have any others right at the moment.
Okay.
Oh wait, one more just came in. I'll let Raj take this one.
Will Spark be completely integrated with R and others? Well, that we are not sure of. There is a lot of work going on that end.
Yeah, there's some work in the Spark community to integrate with R, but I don't actually know off the top of my head what that is. But whatever is done in the Spark community, that's just work we'll support, obviously. So that's kind of something they'll drive forward.
All right. Well, thank you, Alan and Raj, for taking the time to share your expertise around Apache Hive and the Stinger.next initiative. And I want to thank all of you for taking time today to learn about how Hive's new capabilities in HDP allow interactive SQL queries over at petabyte scale. If you haven't signed up for the remaining 6 Discover HDP 2.2 webinars, you can do that from hortonworks.com/webinars. Next Thursday, November 6th at 10 a.m. Pacific time, we will hold the 3rd webinar in the series, Apache Falcon for Hadoop Data Governance. We hope you can join us for that next week. And remember, we will post a blog with any questions that came in last second here we didn't get to. We'll answer those on our blog next week. And this ends today's webinar. Thank you very much for joining.